Hello everybody and welcome back to another video. Today we're going to be going over the heat equation and its properties, as well as the required conditions needed to solve this equation. Now, without any further ado, let's go ahead and get started. So, before I even begin, let's go ahead and actually define the heat equation. It's going to be defined as C times rho as a function of x, partial U over partial T, equals partial x of k naught times partial u over partial x plus q of x t. Now, we'll go ahead and actually I'll go ahead and actually explain what all of this means in just a moment. But for now, let's go ahead and just note this equation down, because again, it's going to be the equation that we're going to be working with for the remainder of this lesson. So now that we have this equation, you might be wondering, Q, C, rho, what does all this mean? Well, to put it simply, the variables Q, rho, and C, and so forth are the parameters of our equation. So let's go ahead and actually define the parameters first and foremost. So as Q of xt, what this is actually known as, in terms of the context of our equation, this is actually known as the heat source. And again, I'll explain a bit more exactly what we mean by this. But for now, let's go ahead and just jot this down, and we can always go. We're going to go back and reference this later during the lesson. So again, Q of xt is the heat source. U of xt is the temperature. In other words, our general solution, right? Because we want to find a function in terms of u of xt, and this is our temperature function, which of course is it's in terms of the x and time variable. C is known as the specific heat capacity. So this parameter deals with essentially how much energy a certain mass of a material, or an element, or whatever you might have, its ability to store a certain amount of heat before its temperature is raised. So water, for example, the reason water is a really good coolant and a really good um, essentially it's a good moderator, it's a very excellent moderator of temperature, is because it has a very high specific heat capacity, which means it can absorb a lot of energy before it itself warms up. So what I mean by this is, for example, um, it will take a lot of energy, like for example the oceans, a big large body of water, for example. um, Part of the reason why areas close to the shoreline and are near the ocean, the reason their temperatures are often, much more steady throughout the year, is because of the specific heat capacity of water. So what I mean by this is that, for example, during the summer, near the coastlines, at least here in California, temperatures usually end going from around 70 to 80 degrees Fahrenheit, um, which again, it's fairly moderate. But more inland into California, say like the Central Valley, or down in the Orange County area, for example, temperatures can reach a lot higher. During the summer, typically we get temperatures of around 100 to 110 degrees uh, Fahrenheit, which again is well over 40 degrees Celsius. And the reason it has to do is because the ground itself it's not a very good, it's not a very good, in a sense, has a very high specific heat capacity. So with all that energy being poured down by the sun for example, during the summer, since the soil itself doesn't have a very high specific heat capacity, instead of storing that energy, what it'll do is it actually use that energy to raise its temperature. Likewise, around the coasts, the water around helps to absorb a lot of that extra energy, and since water has a very high specific heat capacity, it allows for the temperature to maintain relatively moderate throughout the year. Because again, it's the ocean itself is it's a sink. A sink of heat where heat can essentially be stored during the day and then slowly released out during the night, keeping temperatures relatively stable. Our next parameter, rho of x, is our mass density. And this is exactly what it sounds like. Essentially, it's, you know, the mass density of any object we have. Something like a metal will have a very high mass density, where something less dense, for example, like styrofoam, will have a smaller mass density. And again, that's pretty straightforward and self-explanatory. The last parameter, K naught, it's a measure of our thermal conductivity. Again, this should be fairly self-explanatory. Again, what we mean by thermal conductivity. So again, how well an object will conduct the surrounding energy around it. So with that said, and again, these are our parameters. So let's go ahead and just label these as our parameters. So with that said, I do want to talk about a specific case in which, for example, it's a uniform rod, uh, uniform thermal conductivity, uniform mass density, uniform specific heat capacity, etc., etc., etc. So in essence, these are essentially going to be constant. They're not going to be essentially functions of x. It's not going to vary. It's not going to vary. For example, the mass densities. It's not going to vary in terms of the length of like where exactly you are on the rod. Since it's all going to be the same, these are going to be considered constant. So there is a specific case. So again, in the specific case of a uniform rod, again, it implies that C, rho, and K naught are all constants. Then our PDE will look something like this. Again, uh, and again, we also saying that there is no external heat source. It's just a rod by itself. Uh, whatever we just want to model in a sense the temperature throughout the length of the rod, and again, as it also it evolves through time. So in that specific case, since C, rho, and K naught are all constants, our equation will essentially kind of look a little bit like this: partial U over partial T, partial equals partial x, K naught partial squared U over partial x squared plus Q, where again, since we don't have an external heat source, which again is represented by Q, we can just say that we're going to say essentially that Q equals 0. So again, going off this here, um, essentially we can shrink down the equation to something a little bit more palatable. If we move over our constant C and rho over, and then just uh, go ahead and perform that differential operation on our second derivative of u on the right hand side. So what I mean by that is, if we go ahead and divide both sides by C and rho, we'll get something akin to partial u over partial t is equal to k, and I'm going to just label this, and you'll see what I mean in just a moment as capital K, um, partial squared u over partial x. Oh, excuse me. Uh, yeah, so up here, this should have just been, yeah, my mistake. I guess I was getting partial u over partial x. So yeah, okay, that makes more sense. See, so now it makes sense where we're getting this partial squared u from. And again, since plus 0 for our external heat source, that's not going to be an issue. And again, this is a capital K, which again, I'm just denoting as where capital K is equal to the uh, thermal conductivity divided by the specific heat and the mass density. So again, this is where we have this one constant is essentially describing uh, essentially describing this big constant here, as what we originally had in our original equation as the specific heat capacity and the mass density. And so this actually has a very specific name. This term right here. This is going to be called. This is known as the thermal diffusivity. And let me see if I can go ahead and diffusivity. There we go. It's known as the thermal diffus diffus diffuse diffusivity. Um, and again, let's go ahead and box this, and we're going to go ahead and call this equation number 3. Now, some interesting things to note about equation 3. Equation 3 is it's essentially is known as the heat equation, as you could imagine. Heat equation. It really what it describes is it describes how the heat energy spreads out physically throughout the rod, which is known as the technical term for that is called diffusion. So again, it describes the evolution, or I guess we should just say the let's just say the instead of saying evolution, let's say the heat energy and how it spreads out through for example the entire material, aka known as diffusion. Again, that's an important term that we want to keep in mind. So now that we have this heat equation in terms of our thermal diffusivity and our derivative with respect to time, as well as the second derivative with respect to squared, our second derivative with respect to our x-axis. Now, just like we spoke in the previous video, typically when we're solving differential equations, whether it be ODEs or PDEs, to get a solution that we will find usable and that typically will most represent whatever we're trying to model, we want to talk about a certain conditions that will allow us to solve for those specific uh, uh, solutions that we're looking for. So the first of that is that after we get that equation, we need to define certain variables or certain values as well. And the first of that is the initial conditions. So these are exactly what they sound like. They're essentially conditions that the equation, for example, is modeling at a certain point in its and its trajectory. Now, typically we don't need to know every single initial condition. We only need to know the ones that are relevant to our study. And that will allow us to in a sense, then solve for that particular general solution. So again, um, to predict the future temperature, or even the past temperature if we wanted um, to predict the future temperature, we need to specify the initial temperature, which makes sense, right? Because we if we don't have a sense of where we're starting, then we really won't be able to get to where we want to be. So in other words, the initial temperature is essentially the temperature at time equals 0. So again, what is the temperature at t equals 0? Well, the way we represent that in terms of our function is we're going to say, okay, well, one of our initial conditions is going to be in the form of u x comma 0, because again, the x variable is the distance. It's the space variable. We're not talking about the initial condition about a certain spot in space, rather at a certain period in time. Since it's only a function of x, we're just going to say, well, we're going to make this some arbitrary function of x. Now, another important thing to note is that the higher our differential equation or our PDE goes up in its derivative count, the more initial conditions we're going to have. So for example, if we look back at our original equation, we had essentially partial u over partial t. Now that's in essence just one derivative of time. So because of that, since we only have one derivative of time, we're only going to need one initial condition of time. Likewise, if we had, say, a second derivative of time, a second derivative of u with respect to time, we would need two initial conditions, and so forth. So essentially the rule is, for the nth derivative, we need nth initial conditions. And again, if you've taken your past ODE class, this kind of makes more sense. Since typically we would need more conditions again to satisfy the requirements, because the higher the derivative goes, the more peculiar, the more specific it has to be in terms of our conditions. Now, with that said, that does bring up an interesting question. Is the initial condition enough to predict the future temperature? I mean, we've stated that it should be enough, but how do we know? We're just because we have it here. How can we be sure that we don't need other initial conditions? So our question then becomes: is the initial condition enough to predict the future? And again, future temperature. Well, we know that the temperature changes according to our heat equation labeled as 3. So again, that's this one here at the left side box. Sorry about that. So we need to know, so in order to know that, we need to know what's happening at the boundaries, at the edges of such uh, like, for example, so whatever we're using. So again, we know our heat equation, and then again the third equation there. However, simply knowing the initial condition isn't going to be enough to have that uh, general solution that we would like. So we need to know what occurs at the boundaries. At the boundaries, in other words, at aka, again, aka, at x equals 0 and x equals L. So if we go ahead and draw just a simple picture here to try and illustrate what exactly we mean by x and L. So here I'm going to have a simple two-dimensional rod. Again, we're assuming that the majority of components of our parameters are constant, like its mass density, thermal conductivity, and so forth. So let me go ahead and just change this to a different color just so we can see this a little bit better. I guess I'll use red. You know what? Let's go with green. And I'm just going to draw a coordinate system on this rod. We're at the end point here on the left hand side. This is where x equals 0, and on the right hand side, this is where our arbitrary end condition is going to be, where x equals L. And again, if we label our axes, this is x, and we're going to say this is, and let's go back to our original color, where essentially it's a known area. And again, it's a one-dimensional rod. Where at the endpoints, x equals 0 and x equals L, we have to also know what's going on at the endpoints, not just at the initial temperature. So what those are, or essentially what we're asking here is, what are the boundary conditions? What are the boundary conditions? Let's go ahead and... So again, there's a couple of ways to define these, but a lot of times it just depends on the physical mechanism uh, occurring at each end. And I'll go ahead, and again, we're gonna go ahead and explain this a little bit better in just a moment. Exactly what we mean by, like, what exactly we mean by physical mechanism. Um, but for now, let's go ahead and just note this down. And one thing to note is that often the condition depends on the material inside and outside the rod. For example, say your material is a uniform rod of, say, uh, copper, for example. Copper, assuming it has uniform density throughout, it's going to have a constant thermal conductivity and a constant, a constant uh, specific heat capacity, just like we have here in our parameters up here. But what if that rod was not made of a uniform material? What if, say, it was a combination of a bunch of other metals? Say, for example, we had a rod of aluminum, maybe some gold in there, um, whatever you might have, lithium. Each of those have their own individual properties. And so, in order to solve for something like that, um, we have to know exactly what's going on, not just with the materials themselves, but what's going on outside and inside as well. So again, often it depends on the material inside and outside the rod. So the first one of those conditions is what is known as the Dirichlet boundary condition. And if you did watch the previous video, this should sound familiar. We did briefly mention these at at the last video, but now we're gonna go in and exactly explain exactly do we mean by a Dirichlet, Newman, or Robin condition. So the first Dirichlet boundary condition, and we're gonna go and say I'm gonna label this A. The Dirichlet boundary condition. And so what we mean by for example, a system having a Dirichlet boundary condition, is essentially in which one end of the rod is in contact with some sort of constant temperature, external factor. For example, I like to use the example of, say, I have one end of the rod suspended in the air, and then one side of the rod in the bath water, say warm water. So only one side is being heated up, whereas the other side it's exposed to really to in that case, in comparison to the water, it's not really doing much. So mathematically, the way we would represent this is that U at 0t is equal to U sub b of t. And again, if we look back up, this should have been, yes, p. So again, essentially this is saying where U sub b of t is the temperature of a fluid bath in which the rod was in contact. Okay, so again, that seems pretty self-explanatory. Essentially, what this boundary condition is saying is say one end of the rod is in contact with some kind of fluid bath, whether it be some liquid or air. I just like to use the example of water at a certain constant temperature, just because that's usually the easiest to associate with this kind of with essentially this boundary condition. The next boundary condition is that here we prescribe the heat flow. So what do we mean by this? So let's go ahead and just write this down first. Okay, Newman boundary condition. And here we prescribe the heat flow. And again, we're going to go ahead and talk about exactly what this means. But for now, we're going to say, well, how do I how do I how do I write this mathematically? So again, partial u over partial x, 0 comma t, is equal to some function of t. And again, what this is saying is, if you look at this equation, you see how for our space, for x, the x variable within this equation, essentially we're prescribing it to 0, such that our remaining function will only be a function of t. Now, there are a couple of special cases of this specific condition. So for example, if that set temperature is equal to 0, then this would imply that our partial derivative with respect to x of our function will also be 0. And essentially what this is saying is that there is no heat flow on one side, on that particular side of that, rather there is no heat flow going throughout the rod. So, mathematically this is how we would represent it. But in more typical speak, we would say that this would be considered perfectly insulated. Again, which makes sense, right? Since if the heat flow is 0, heat is in a sense is not going to be traveling from one point to another. It's only going to be evolving through time. So we say that's perfectly insulated. Now there is another example of this. So if a problem with Dirichlet and Neumann boundary conditions, it is said to have what is known as mixed boundary conditions. So again, if we look back at our Dirichlet, it's essentially saying that the temperature at one side is for example, was in contact with some fluid bath, and say one side is also perfectly insulated. So imagine a rod where one end is dipped in some constant temperature water, and another end is insulated with, for example, say styrofoam or some kind of insulating material that prevents a lot of that heat flow from transferring much to the side. And finally, if at the edges we're essentially having we have no heat flow, then the boundary condition is said to be homogeneous. It's said to be homogeneous. Okay? So, again, that's for our Neumann conditions and our Dirichlet conditions. There is one more. Of course, if we recall from the previous lecture, the last one is the Robin condition. So, when is this Robin condition used, and how is it different from the previous two that we had already mentioned? Well, a Robin condition is used when a boundary condition is in contact with a moving fluid. Is in contact with a moving fluid. And again, that fluid could either be, water, air, whatever, whatever in that condition we would require it to be. So this is also known as convection. And the good example of this that I like to use, personally myself, I'm big into PC gaming. I'm really big into building my own computers, and one thing if you build computers is that you want to keep the system running as cool as possible. And the way you do that is often components are essentially, we add what are called heat sinks to our components to allow for a faster transmission of heat. Now, this in of itself is actually a perfect example of the heat equation, but to put it a little bit more, I guess, to put it for something that's more visualized, um, we can imagine that, on a PC motherboard, we often have this processor, for example. Ooh, that's a really bad processor. Let's see if I can draw this a little better. There we go. So, it's some kind of small rectangle. It produces heat as it does work, obviously. So let's go ahead and actually, there we go. Now, typically what we like to do, or what is rather, most computers do this, is that usually something like a copper shim or some other material, uh, whether it may be, whatever it might be, um, and again, I'm just gonna, for this copper shim, I'm gonna just dot it in purple, just so we know the difference. But that's then usually attached to something else. Um, Typically some heat pipes that often just end up going to a radiator. So again, we see that the source of the heat is here. Typically, the copper shim or whatever we might have there helps to conduct a lot more of that heat than it would if we would just place the cooler um, on the directly on the processor itself. Now, typically, um, computers also have, and pardon, pardon the terrible drawing, but you know, a fan that usually takes in energy one way, takes in air, and then releases it out another way. So this convection allows the metal to cool itself with the air. Again, a moving fluid, to allow for then our processor to also keep cool. So this is a really good example that I like to use when thinking about these conditions, especially the Robin condition, because it's something that for me personally, I see this every day, since I'm a really big PC gamer. So this kind of stuff, it's all over. It's all over. It's not just some abstract thing. It's just how the question becomes. Sure, we know that this exists in our real world, but how can we transfer that into a mathematical concept? And that's what the heat equation essentially is doing, is that we're treating the concept of heat dispersal, if you will, as a mathematical concept to then be able to predict, or even from the past to the forward, what our temperatures might possibly be. And engineers use this a lot when trying to design new systems, because they want to see, okay, given a certain cooling solution, how much energy, how much of that produced heat can our machine, uh, dispel? Because again, if the rate that the machine dispels heat is lower than the rate at which it generates it, obviously that's going to be bad, because uh, essentially heat is going to be building up in the system because it can't get rid of it fast enough or efficiently enough. So how do we? So with that said, how do we write this in more mathematical terms? Well, we have an equation. So not surprisingly, so again, we're going to have our constant partial u over partial x at the origin is equal to some negative h. And again, I'll explain what this h constant is. U of 0t minus u b of t. So what does this say? As much as I like to say this, what the heck does this all say? Well, here is this side essentially is saying that the heat flow leaving the rod And again, on this end, it's essentially saying that it's proportional to the temperature gradient of the bar. Again, that's what this u of 0 comma t minus ub of t. Again, the temperature gradient between one end of the rod and then the initial end of the rod, and the external temp. Okay? So let's go back to our original color here. All right. So believe it or not, this equation here that we have is actually a more generalized version of Newton's law of cooling. Where again, if we remember from the very first, from the very first video on this topic, uh, Newton's law of cooling was typically represented by a differential equation that is proportional to some constant times the temperature. So believe it or not, again, this is a much more generalized version of it. And again, I was going to say that we're going to go ahead and define H, where H is defined as the heat transfer coefficient. Okay. And again, we'll go ahead and explain in later detail exactly what a lot more of these terms mean in just a few more videos. But for now, we just want to go ahead and get just the general idea and how we would represent it mathematically. So again, since this is essentially our scaling constant, we can say that this sets the equation's scale. All right. All right, guys. So I know this video is getting upwards of 42 minutes long, 43 minutes. We have just one more thing to cover in this particular video. We won't cover a specific example, at least not in this video, because I feel like the video is already getting too long. So again, we're going to go ahead and do a more of a real world example in the next video. But for now, let's go ahead and just finish up the content for this this last lesson. Okay, so now that we know that, the next question arises. Okay, so we have all this information, sure, but how do we then know if, say, we come across on like an exam, or say we want to formulate our own heat equation, how do we know whether a PDE is properly defined? Because we might have a PDE, but we could be missing, say, the initial conditions. We might be missing part of the boundary conditions. So in that case, it would actually be a lot more difficult to solve. So again, the question we're posing essentially is, what should a PDE have to be considered properly defined? And the answer to that is that a properly defined PDE, it must have the initial conditions and some set of boundary conditions. So again, this is a little bit different from our ODE class, where our equations typically only needed the initial conditions, and we didn't really talk about the boundary conditions because they weren't really necessary in those particular cases. But again, if we want to know that a PDE is properly defined, we need to have a set of initial conditions and a set of boundary conditions. So again, the way we would write that mathematically is, let's go ahead and go back to our equation, the heat equation in full. So C times rho of x partial u over partial t is equal to partial x of our constant k naught partial u over partial x plus some external heat source in terms of both the time and this space coordinate. And again, let's go ahead and just box this. So that again, this is our heat equation. Whoops. This is our heat equation. And this is true for between the lengths 0 to L, like for our rod, and for all times that are positive, where our initial conditions are defined as u of x, remember t naught, the initial time, and we're going to say that's some function in terms of x, and our boundary conditions, u of 0 comma t is equal to 0, which is equal to u of L comma t. So again, in this specific case that we're mentioning, because both of the boundary conditions are 0, it is said to be homogeneous, at least in this very specific example that we're giving. So again, this would be known as the heat equation with homogeneous Dirichlet conditions. And that's all she wrote. So again, for the next video, we'll go ahead and go over a more general example, one with that we're actually going to be doing a little bit of calculus and some math about it. But you'll be quite surprised at how, it really isn't that bad. Once we actually do try to find the solution, as long as we do have, again, the heat equation, we have our parameters defined, and we have at least an initial condition and a set of boundary conditions. So again, guys, if you guys have any questions, please feel free to drop a comment down below, or go ahead and PM me, and I'll be sure to try and respond to as many people as I can. So again, for next time, we're going to be going over a real world example again. And what I mean by that is just we're actually going to be defining values to our constants, like for example, to our temperatures, to our constants, etc., etc. So hopefully that'll give us a better idea of how exactly we can use this heat equation to derive a general solution for the temperature throughout some length of space and some duration of time. So again, guys, that'll do it for this video. And yeah, I'll see you guys in the next one.